Okay, so for our project, we did the Nutley on-ramp onto 66, and our central question was, what is the maximum safe speed for driving around a curve in a car? So here we have our diagram of the on-ramp, and we found that the radius is 45.88 meters, and the force acting on the car is force of friction.
So this is our free body diagram. The forces acting on the car are the road, which is pushing up on the car, which would be the force of normal, and gravity pulling down on the car. And for every action, there's an equal and opposite reaction. So the car is pulling up on the earth, and the car is pushing down on the road. So the force of friction is pulling right on the car towards the centripetal force, and that is the only force acting on it on the x-axis. So Fn is equal to F of g, and you can tell that they're balanced because the car is not pulling down and it's not floating into space. So that's it.
As our variables, we have r for radius, which is 45.88 right here. Then we have our coefficient of 0.8 for a dry surface on a dry road. Then we have the equation for the force of the centripetal force, which is mv squared over r. And then we have velocity, which is 19.60 meters per second on a dry surface. So for the maximum velocity in a dry road, we established that Fn equals Fg because they are balanced. The only force acting on the car and on the x for the x forces is force of friction, and force of friction equals the centripetal force. The sum of the forces for the y value is 0 because there is no acceleration. So the force of friction equals the mass of the car times gravity times the coefficient of on the dry road. So force of the centripetal force equals mass times velocity squared over r. So we plugged in the values. We plugged in 10 meters per second, 10 meters of second squared for gravity, and then 0.8 for the coefficient of friction for the dry road. We got mass times 8 meters per second squared, and we equal it to the equation of the centripetal force because the centripetal force equals the force of friction. So then we plugged in 45.88 for the radius, and then because m is on both sides, we cancel them out. Therefore, mass does not matter in calculating maximum velocity on the dry road. To even further isolate v squared, we plugged in the radius, which was 45.88, and we multiplied it on both sides, canceling 45.8 on this side, and then multiplying on this side. So if you're multiplying 45.88 times 8 meters per second squared, we got 367.4 meters squared per second squared, which equals the velocity squared. We got square root it, and then velocity equals 19.60 meters per second.
So we originally picked Nutley ramp onto 66 because on the way to work on the project, Sophia and Melvin spun out. And so the road was wet, so we wanted to find the maximum velocity for it to be safe. And so basically the coefficient is 0.4, which is half of the coefficient of friction for the dry road. And steps 1 through 5 are the same, and the rest of the steps are also the same, but the coefficient is different, and in the end it's 13.55, which is less than the one for the dry road. So overall, if the road's wet on a curve, you should slow down, and yeah.